I will start with something that's very much like Shakespearean play. Cvitanović will play Cvitanović within Cvitanović. That looks hopeful.
So this is done in Germanic style. So review part one. We just review dynamics. So this is something everybody knows. And for that reason, it was very short. It took several months. The idea is there is something you act on. There is something you act with. You have to worry about symmetries or enjoy symmetries. You have to worry about neighborhoods, stability. And finally, we went global. And that was done by looking at unstable manifolds. So this is all elementary, and it is, except maybe some part of the symmetries reduction are not well known to the best of my knowledge, but everything else should be in introductory courses in nonlinear dynamics. And why did we do it? Because we know that typical dynamics, there are two very romanticized cases. Typical dynamics is integrable. It's like a clock. That happens in approximately when we look at planets going around the sun, but other than that, it almost never happens. So that was a romantic thing. Then the next romantic thing is to say, typical dynamics is like a bouncing ball in the billiard. That's called fully ergodic. That never happens either. But it's an example of the other extremes. So either there is only stable motions, which is counter nature or our experience, or there are only unstable motions. So small perturbations have huge consequences. That's more in line with our experience and less in line with what we are taught when we go to physics at school. So our goal is to understand what to do, not when the world is integrable, that's you learned in your classical mechanics courses. Our goal is to learn the other thing. What does the world look like when it's not so simple? And that's why we did all this. We needed the tools to be ready to do part two. And that's the wonderful world in which chaos rules. Why is it wonderful? Because chaos is the source of all creation. If the world was just a clockwork, it wouldn't be worth living. So all the wonderful stuff is of this nature. And here, this is just a view of differential equations. So, I don't think there's a single idea that you don't know in the whole introductory part of the course. But at this point, there's an idea which is almost on par with quantum mechanics. It's certainly on par with statistical mechanics. And the idea is a realization that it doesn't make sense to follow very precisely a single state, because this is undoable. We learn it by looking at how neighborhoods and how unstable manifolds. This is useless for anything that's longer than Lyapunov time, and Lyapunov time might be rather short. So for argon molecules, it's 10 to the minus 27 seconds, let's say. I forget what it is. It's a fairly short time. Even our people in the basement cannot see that. And if it's fluids, maybe it's a second or a minute, and then you lose all the information by that time. If it's solar system, it might be 100,000 years, but you don't know what's going to happen in 3 billion years. And you might care about long-term past and future. So depending on the problem, this old-fashioned physics department way of thinking that everything is linear and you do something might be useful. And for other problems, you really have to take them by the horns and look at them, and that's what we're trying to do. I'm just giving you tools how to approach your research in case where you see things being unstable and unpredictable on the time scale that you care about. But you have laws of motion. It's not chaos in the sense of being ignorant, it's just chaos in the sense of losing control very quickly.
I'll try to give you some flavor of what's ahead now that we have basic tools. So, upon further reflection, turns out that we're thinking about it all wrong. It seems to be the story of my life. I learned something, then I learned that it's all wrong. It has limited application and, it's deceptively attractive, but very powerless. So, what did we do wrong? And once you learn this, you realize it applies to everything, including, your harmonic oscillator, integrable systems. Never, ever will humans specify an interesting initial condition of a system to infinite precision. It's impossible, and it's not a good idea, because even if you could do it, this is a model that's the finite precision of something that has many more degrees of freedom you're not taking care of. So it's not a good thing to do. What you have to do, and again, we kind of knew this since Boltzmann, roughly speaking, Liouville, Boltzmann, etc. Anything that you can look at is actually a little blob of state space points. So you have to think about the densities of initial conditions. When you're doing something in a good experiment, maybe you produce a density that's a very peaked Gaussian, but it's never a Dirac delta function. That doesn't happen. Dirac delta functions, in what I'll explain now, are built into assumption that the laws of nature, deterministic laws of nature, are exact, infinitely precise. And even that you can relax, you can allow some stochasticity of laws of nature, and results of what we have thought about in nonlinear systems and now will be still robust against that. So when ergodicists, who are people who get salaries to study this stuff as a lifelong obsession, describe dynamical systems, they never describe it as space of states and something doing to them. They also always add a third feature, which is some Greek letter and which signifies measure. There's a say, how do you actually observe these things? And the way they do it, it's pretty incomprehensible, but I hope I'll give you a sense what it means and how to do it. And the result of this way of thinking is kind of miraculous, because what happened today is we started with nonlinear dynamics. We said, there are other things in the world than harmonic oscillator. There are things that are anharmonic. They have dependence on the state you are in a nonlinear fashion, etc. And almost anything is nonlinear. So nonlinear science is incredibly stupid name. It's like if you took biology, and here I'm quoting an Italian colleague, if you took biology, you singled out elephants and you said, here we have elephants, in other words, harmonic oscillators and Kepler ellipses. And here we have non-elephants, which means everything about the elephant. That's what nonlinear science is. It deals with everything. There's very few things which happen to be clocks, but everything else is not a clock of infinite precision. But here we are stuck with a stupid negative name for the subject. Not my fault. So how do you actually, explore these nonlinear systems? That's called measure. And here is a definition. We say at point X, there is mu for measure. And for physicists, it is good enough to say what I mean is that in the infinitesimal volume in d dimension, dx, I have a function which is a density function. And what is this density? Well, the way we think about it is that if I can specify not precise point, but the neighborhood in which I am, then I can take some number of points in it and involve them. So it's a density of what might be called a representative points, meaning representing the dynamics of the flow of points. And this density, because we are in a dynamical, time-changing world, in general depends not only on where you are, but at what time you look at the density, how many neighbors you have this in it. Another way to say this is that you can never look at the world with infinite precision. You can only think of it as coarse-grained. The way to define coarse graining is to introduce something that statisticians and other people call characteristic function. It's like a Heaviside function, but it's not. It's defined for arbitrary dimensions. And it says that if I look at point x, I can associate with the simple function chi, which is 1 if x is in a neighborhood whose name is I, some label, or 0 otherwise. For example, I can use numbers to label neighborhoods. So if this is a state space M, then I can call this neighborhood 0, neighborhood 1, neighborhood 2. And what I've done is I've partitioned or coarse-grained the space into 3 very coarse grains, union of 1, 2, 3. But if I want to be a little more careful, maybe I can subdivide each one of these guys into 3 unions, and I'll label them 0, 1, 0, 2, 0, 0. And this is very much like when you took a parabola and looked at neighborhoods which are on the same side once, twice, 3 times. So this is called symbolic dynamics, and sometimes you can do. So this guy gets divided in 3 neighborhoods. This guy gets divided in 3 neighborhoods. And they are finer, now I have 9 neighborhoods. So they give a better, more precise description of the space. And then with each neighborhood, I can define coarse-grained weight, which is, how many of these representative points are in it, which is the integral over whole space, d mu. So, all possible, well, d mu x, this thing here, characteristic function chi x, that just picks up non-zero contribution from the neighborhood I, d mu x. And this is, the density I have integrated over either this neighborhood or that neighborhood, smaller and smaller neighborhoods. So that's the idea of coarse graining. It's totally essential concept for statistical mechanics. Now, I might choose 100 initial points, but you might choose 11,000 initial points because you are better computing. So the measure has to be normalized. That's the only sensible way to compare our results. So the way you define these measures, if you have 1 kilogram of initial points and you have 27 decagrams in your particular area, the ratio of those is a pure number, and the total sum for normalized thing, or coarse grain version with n divided into I neighborhoods, should be 1. Now, as we make a neighborhood smaller and smaller and smaller, we have some intuition that might be not correct for ergodicists, but it's correct for physicists, that my distribution of necessity is smooth because I cannot prepare very kinky distributions with arbitrarily small kinkiness. So the function I'm evaluating is small. So as I decrease the area on which I'm evaluating it, it might make sense to approximate this by evaluating my density just at a single point within the area, like at this point here, and multiplying it by the volume of the area. This is two-dimensional, so this is area, but the volume of partition in 3 dimensions will be 3-dimensional volume, so this is volume. And this is just the point. And we do this for each partition, and then either mathematically or by cheating by publishing a Fizerev letter, we pretend to take the limit to 0, which means that this resolution, this was first level, second level of resolution, infinite level of resolution as a property, that all these volumes go to 0, and I'm actually exploring the density in that limit as a continuous function. So now comes a trick that nobody asked for. It's crucial. See, when you think of densities, when you think of statistical mechanician, you're given a map of where everybody is at some instant of time, and then you measure how many little guys are in any given neighborhood, and you get some estimate of density function. So that's a kind of static picture. But these densities have a reason to be there. They came from dynamics, something was happening. So what was happening was that there was some initial space a ball, d-dimensional ball, on which I stuck some amount of so-called measure, mu I. So this is a ball whose name we call I. And now, if I take any point in this ball, after time t, I'll land someplace else. So everybody here is going to, move. We call it a flow rather than just a trajectory. And after time t, the law is assumed not to be discontinuous, so not giving random direction to random people, just telling them, go in this direction roughly, the way I tell you. And what happens is that this gets deformed. And the original ball becomes a deformed ball. And we can call this function of mu I. So, well, our function in time t, so this was x at time 0, this guy, this is x at time t for everyone at this point. We can move the whole sets of points in one go. Now, there is a very important conservation law here, because in dynamics, we're not allowed to destroy or create trajectories out of nothing. in deterministic dynamics, every state space point has infinite past and future, and it's not destroyed, it's not created, so there is a mass conservation. If each one of them weighs a gram, the number of grams or kilograms is unchanged by flow. So that's a very important thing. There's a continuity principle. And we can phrase it in the following way. We can integrate a time t over this volume here. So I started with mi, and now I ended up with a big volume. And then the density will be some function evaluate time t. But that must equal, so this is initial volume, that must equal, because that's just adding up everybody who was here, that must equal the original volume. The original volume was I integrate here over coordinate dx at time t, and I integrate over undistorted state space volume. Now what I can do is I'm allowed to change the new coordinates here to the original coordinate dx zeros. And to do that, I have to pay a price of a Jacobian. Remember that we define the Jacobian of the flow to be, if I vary the initial point j, what happens to the final point t? There was a matrix of, what happens to variations in all the points, varying initial, getting final, that's called Jacobian. But if I change the coordinates from these one to those ones, meaning coordinates which are restricted to this initial volume, I pay a price, and it's determinant of the Jacobian. It's just the usual coordinate change. So mass conservation gives us a nice result immediately. Very simple one. It says if I had some density at initial time, and I would like to find density at any time after that, xt, well, I just do this change coordinates, then it's integral or same regime, so integral should be the same. So I find out that the density simply changes as determinant of Jacobian of the flow, where, x at time t is just the evolution from initial point to the point t. And that makes lots of sense when you look at it. It says density is inversely proportional to volume. So if this volume gets spread out into larger volume, then there'll be less density per unit thing. And if it gets into a smaller volume, so this determinant is more than one, then the density will increase. So that's very simple. So it turns out, if you think in terms of densities, you have a very simple rule how the densities changes. And I wrote something, there are two mathematicians from 19th century and word operator. Now, operator is always a scary word. My advice is whenever somebody says operator, say, oh, a matrix. But, on infinite space, I have to be careful. So what is the operator, Perron Frobenius operator? It says, I start someplace with some density. I operate on it. This is the operation the dynamical flow did to the density of trajectories. And at time t, I measure a density. So this is variable I measure in time t, which is usually different from the initial density. If it's the same, we're dealing with volume preserving flows, which are fine, but they require special discussion. We will not do it right now. And how did this happen? Well, I started with a density at the beginning, so I started density computed around point x0 here. I went time t. So I start with the density at time 0. I go time t0. Now, because this is determinism, there is only one outcome of this, because every trajectory is unique and definite descendants as time passes. And that's coded by a Dirac delta function, which is a function that has property that it's non-zero exactly when the point I'm looking at now had arrived from initial point by deterministic flow. So that's a different formula for density than the one that just I gave you, but it's perfectly fine. It codes how dynamics changes that density. It says every trajectory that starts someplace ends up at point X, a unique one, and it carries with it that local piece of density and puts it there. Now, Dirac delta function is defined operationally that if I have some sub-volume of the state space, then delta x is 1 if x, this integral of delta x, if x is in that neighborhood, and 0 otherwise. So what does this mean operationally? Here I have some kind of function, could be arbitrarily complicated, but I will get contribution only if this combination equals 0, meaning if initial point evolved as a trajectory coincides with the final point. In other words, I'm looking in one dimension for a moment. This is an arbitrary dimension. At any function of x integrated over some volume. And if I plot this, so let me write coordinate x here. And let me write this function h of x. And it's some function that, as x varies, crosses 0. And this is a non-zero only for values of x such that h of x equals 0. Now, what happens at that value, I have x minus x prime h prime of x. So if I expand x in the neighborhood of this thing, the first term is 0 because it's 0. And the next term is derivative. Just the first derivative. And I find out that this is 1 over derivative of function x. Absolute value because this is always positive. So basically, I get at 0 to the linear approximation, get delta of the first derivative times distance from the 0. And I have to multiply x by inverse derivative and put it in here. So I can use this rule that this becomes 1. And in the process, I pick up a Jacobian. This is in 1 dimension. In d dimensions, the rule for integrating delta function of any function that has zeros, simultaneous 0 in all the dimensions, is 1 over determinant dh. And now you realize, that's the same rule that we obtained from conservation. So we just verify that this definition of action that produces the new density from the old density is consistent. Gives me the same answer. It says that every neighborhood where I get to 0, I get weight which is 1 over determinant. Okay, why did I need to introduce this stupid Dirac delta function when I already know the answer, right? Well, we went from this initial idea that, we sit here, then they say 10 minutes is up, measure the density, go, measure it. We actually decided to incorporate the process of creating the density into description of it. In other words, we now have an operator that takes a density at initial time, operates on it, lambda tau, and returns me density at time t, which happens to be the correct definition, all x 0 such that they land up after time t, so they're pre-images. There's a minus t, which I'm not writing very well. And the final point, and each one of them is just pieced by taking the original density, x0, and dividing it by the derivative of the map evaluated at that 0. So that's in 1 dimension. That's in d dimensions. And now that's an operation which says if I know the law of motion, I can give this a name. Everything we don't understand in physics, we give it a name, and mathematics, and call it L, curly L, to signify operator under a matrix that says I start at point X, I end up at point Y. And because this is determinism, I use my deterministic law to propagate the initial point to the Y. Then I make sure that this thing is non-zero only when I get the right answer. So that's where determinism comes in. If you met operators in quantum mechanics and statistical mechanics, it's not so sharp because an initial point produces a wave function or something. So that's written differently. But for determinism, there's only one answer for any initial question. And this has a name, 19th century again. And the way you think about this, this is a bunch of letters, at least they're not Greek to you, but this is really whenever a function has two, whenever you have a function of x, when you discretize, it becomes a vector of points. If you have something that depends on two continuous variables, when you discretize it, it'll be a matrix. And anytime you actually do anything, you do any real work, you will discretize because computers don't like infinite quantities. So it's just a glorified matrix, and its purpose is to move densities around. It's a nice thing because to have a matrix, you have to have a property that when you take a matrix, multiply it by another matrix of the same class of matrices, same dimension and same thing, you get a matrix again. That property is called semigroup. Semi has to do with the detail that in dynamical systems, we like to step forward in time, and we are not always guaranteed we can step backwards. So it's a group, but it's only in one order. And these operators have a property that if time is zero, nothing has happened. They act as identity. And people, it's a free country still. You're still allowed to ask questions. Enjoy your privilege, do it. It has the property that if you evolve sometime, and then you evolve again, you can easily verify that, multiplication of these two guys at two successive times is the same as going the whole time. And semigroup says, we like not to go back, so they're positive. What does it mean to compose two of these guys? Well, we have now explicit representation of how this operator asks on the density, tell me what's density time t later at point y, and the definition was that it's a matrix, a Green's function, whatever you like, evolution operator, that says this is the matrix, in quotation marks, times a vector, because this is a one-dimensional array of values of this density. If you have to do two of these guys, what you do is, what does this mean? You take lambda of, z, y, time, t. You take lambda of y, x, evolve for time t prime. And then multiplying two matrices means you have to sum over this index, but because this is integral, it's written as dy over m. And because these are delta functions, you'll easily verify that when you do this integral is trivial. Delta function is 1, integral delta function is 1 in the correct variable, that you will get lambda t of z started at x, having gone the sum of the two times. So it has a group property that if you compose two of this operation, you get somebody in the same group, just with a different parameter, which is, what you mean by groups. Multiply group elements and you get another group element. So that's one thing that's nice about this operator, which is not obvious in our original discussion, saying we just get Jacobian for the density. So that's how we sneak in operators. And now comes a very important notion, which is the notion of invariant measure, stationary or invariant density. It's a very special kind of density. You look at the time 0, you look at the initial time, and what do you know? It doesn't change. It's always the same. So that seems to be like a nice thing. So this is, in dynamics, first thing we learned, if you have state space and things move around on the dynamics, first thing you always have to do is find the fixed points. These are things that don't change in time, so they're points that change time. It turns out in the space of densities, there could be densities that don't change in time. So there, densities of function. It has a different value at every point in a state space. So it's an infinite dimensional object. But you still have a notion of fixed point in the space of functions. That's very nice. But now that we know so much about dynamical systems, it is an eigenstate of Perron-Frobenius operator. How is so? Because if I start with some density at time 0, and I evolve it time t, and I measure it at point x, I know that this can be done as Perron-Frobenius have explicit expression for that matrix. It's a delta function of initial point evolved, go time t, compare with the final point. Only if the two agree, you give a contribution. And now this is 1 times the original thing. In other words, this distribution is an eigenstate. It doesn't change, but also it has a nice eigenvalue. It has a unit eigenvalue. Now, how could we prepare such a state? So here is one prescription that should work, but has one little weakness. Let's start with initial distribution, any distribution, almost any. There is a set of measure 0 of crazy kinky distributions at times, but anyway, any kind of generic distribution. You write some sine, cosines, polynomials, Gaussians, and that's what this is. Evolve it for time t. Check where it ends up. And now we do this for all initial points, and we take a limit, t goes to 0, to infinity. Now, if I've already gone off to infinity, if I apply operator again, I add a little bit to infinity. In other words, I don't change that. So this is by construction something that's invariant. So let's give it a little name thing. That's a natural measure. So this is actually how we prepare these things in computers if you don't know anything else. We start with lots of initial points and we run the systems for long as you want to. And we have seen this when we are looking at the unknown strange attractor. We found out that after a while, the distributions of the points that describe strange attractor don't change because they're on limit set. We didn't realize that densities don't change, but it should be obvious. So this kind of invariant measure is called natural measure. Natural because that's what you get when you just let your computer naturally do its thing. You just ask computer to iterate many times or integrate a long time. Out of this comes the density, which is called natural measure. It's a density, so it's a function. It doesn't depend on time, so we can drop time index. The two weaknesses, but one is obvious. We start with initial condition and we get something. Definition is this is a limit for infinite time, which we cannot do, but we can try our best. Integrating a delta function of initial thing. And what this does is, it kind of moves the delta function all over the place. Maybe it's easier for you to understand in discrete case. In discrete case, you have n time steps and you increase them. And what happens is you average over them. So you iterate once, twice, until n minus 1 times. And every time you evaluate a delta function of where you are k times later. So now that's a cute formula, but do you really want to do infinity of deltas, Dirac deltas? Especially when you don't know what even one Dirac delta means, because it's a singular distribution, which is either 0 infinity at the point itself in such a way that it's integral over it 1, but So when you do this computer, you don't choose magical point, you choose a generic point. And this tends to work. So that's a good way to compute. And the result doesn't really depend on the initial point. It might depend if you have disconnected pieces of state space that you can go from here to there. Then, there might be some label having it's restricted to something. Now, it could be so that, for example, your x0 was precisely a fixed point to infinitely many digits. Then you would get something, but what you would get is you would just get average over that point because nothing happens. So while a computer does this, there's some dangers in it. So the other thing that you can do easily if you're computing, you don't actually know how to stand exactly at the point, and there is a 0 probability that trajectory will hit some point unless there is some amazing principle that works. You can only coarse grain. So in practice, you divide the space into partition it in the same way we did when we were computing fractal dimension and like nonsense. We partition it as many subvolumes as we can. Each one has a name. And then I can assign this natural measure computed as a limit in time by finding how much time, what fraction of the time I spent in neighborhood label I, and divide this by the full time. That will typically be a non-vanishing fraction, so you can use visitation time to assign likelihood to be in a particular neighborhood. And that gives you coarse-grained natural measures. So this is easy to say, and it's easy to compute. And I want you to experience at least once, it would be nice if you compare yourself, how horrible this is. So this is, mathematicians versus working people. My dynamic doubles in mathematics, who are very appreciated, recognized, etc., prove theorems. They prove theorems on measures being continuous and da 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 da. If you do it on a computer, what we showed you for a known attractor is that it's a map of plane to plane, so variable x and y. Let's say this is 0, and the 2x is here. And we showed you that attractor is something that looks like a horseshoe. It's actually infinitely bent onto itself. So when you look at details of it, you find out that it has a fractal structure that every enlargement shows finer and finer detail. And we only look at the points. We didn't do this natural measure thing. Now, if you do the natural measure, what you'll be doing is on every part of a tractor that to given coarse resolution is visited, you'll put a little box here. So you'll find something, and maybe you'll be normalizing it. And what you'll find is that close to these turnarounds, it tends to peak, and other places it doesn't. And if you waited long enough, could be 1 billion years with infinite precision, if it so happened that one of these peaks went off to infinity, that would mean that you have a delta point. You have a tractor, a periodic or fixed point. If that happened, then the system would not be ergodic, because ergodic means everybody runs away from everybody. Nobody's attractive, nobody's stable, everybody's ugly. Not ergodic. And that means that if you try to describe this measure by anything that seems reasonable to you, it's an impossible task. It's every place non-differentiable. It's every place arbitrarily peaked. Might be even something that dies out and becomes through delta function. This is horrible. And this is wrong. It's a stupid way to think about it. And this compelled my friends and me to write Chaos Book, which so far is hidden from the Strogatz textbook I. And Chaos Book was written to reassure you, to say, this stuff, you never need to use it. Trick is, instead of constructing it, you use dynamics to do the job for you without telling you how it does it. But these measures you never look at. So this is unnecessary, even though this is much of mathematics, of ergodic theory. It is just a distraction, because this assumes that you have infinite resolution. Any coarse graining or anything to do with finite precision or noise, it all magically goes away like Cheshire cat's grin. So what do you actually care in the, as a working person? Suppose you are looking at a frog heart and you need to measure its mean pumping rate or whatever you want to measure. So that's called an observable. It's the same notion as you might have learned in quantum mechanics, but you don't need quantum mechanics on it. It just says, if things are chaotic, rapidly changing, I cannot predict the future, but from my understanding of dynamics, I can give you predictions of things that you want to measure. So when we have an observable thermometer that says Atlanta temperature right now is 16 degrees Celsius, we can do it over all of Georgia, let's say, if Georgia was isolated from the rest of Confederacy. And so we integrate our enclosed state space. And we know what's the density of my thermometers at, my trajectories at point X is being usually natural measure, but it could be some other measure. And then I do my temperature measurement, and this tells me what relative weight this has to do in different parts of Georgia. So that's called space average weighted with density A. Now, if you're doing this over partitions of the space, and that's the only thing we obviously can do, then you actually add up over volumes of subspaces, and on each one of them, you do your best estimate of what the temperature is. So that's one thing you can hope to predict if you understand chaotic dynamics. Other thing that you can do, you can just, instead of going all over Georgia, you can just sit in Hawaii and watch the world go by. You're on top of the Hawaii and you have a thermometer you're holding in your hand and the weather comes by. That is called time average. So I'll use a bar to be a time average. And it depends where I started. But it's defined to be observable at time t, having started at time 0, time tau, integrated over all tau from start of my measurement to when I give up t, average over that time. And ideally, I would like to get an estimate for infinite time because that'll be an invariant estimate. So that's a space average. You have probability. That's the time average. You just let the system run. Now then, there is a bit of mathematics, which is maybe intuitive, but it's not obvious how to prove this, which is that if this trajectory, f of tau of initial condition, is ergodic, that means that your trajectory comes to any neighborhood, open neighborhood, infinitely often. Then this average is constant for any initial point. And in that case, space average, this one, this rho becomes a natural measure because natural measure we obtain by just iterating ad nauseum. It's the same as iterating ad nauseum, integrating for arbitrarily long time. So these are kind of things we can hope to obtain if we had a theory of chaos, which we actually do. Where are we now? Now I've gone beyond Strogat's book. The summary of where we are now is that we have replaced nonlinear evolution of starting at point x0, using our law to run to xt. So that's how we started. We looked at points. And after some reflection, we found that, let's say in 50% of cases, but in lots of cases, the neighborhood of this point was unstable, which meant the outcome is unpredictable beyond the point of time, the time at which we lose all of our initial accuracies. So that's what we have done in Strogat's book so far. Things fell apart. But now in the next chapter, we replace this by linear evolution, because look what this guy is. What it does is it takes a density, does something to it, but doing something to it means it just multiplies it by numbers, it rearranges it and produces new density. So on a space of density, this is linear operation. Nothing depends on density square. And that's very nice. because, we don't know much, but we certainly know how to solve linear problems. So if I start on some kind of, state space, and I plot this scalar function, which is called density, I plot its values, it's positive between, well, it's at least positive, probabilities should be positive. So it's some function every place. And time t later, I end up with a different density that looks slightly different, but operation is linear. I just banged it by something that was glorified matrix. So, this is nice. Nonlinear problems are hell. Linear problems we know how to do. Google ranked matrix or whatever linear problem you like. And it has distinctive quantum mechanics flavor. So it precedes quantum mechanics by 30, 40, 50 years. And what it does is it moves probabilities that you're someplace in a state space instead of probability amplitudes, which are roughly speaking square roots of probabilities. But other than that, it's very like quantum mechanics. And, one of the reasons why we know how to do quantum mechanics, because we know how to do linear problems. And, you might have worried, why is quantum mechanics linear when it describes motions of, bodies that interact with things like Newton or, inverse distant laws, etc., very nonlinear things. Well, there's a price. They never told you this in quantum mechanics courses. It becomes expensive because we had traded three, let's say, Lorentz equation, nonlinear equations, three dimensions, nonlinear equation. And by going to densities, we now have infinite dimensional, but linear space. And it's a function space. That's why it's infinite dimensional. The original thing that we got from Newton was a fata morgana, because this assumed understanding everything to infinite precision. In real life, you never do. And the correct description is the one that I'm giving you now. It's Perron-Frobenius prescription. But it seems harder, but it's actually the only way to proceed from now on. And there was no glimpse of that in Strogat's book, because it really takes literally their trajectories and that's all there is to it. No, that's not the way to describe the world. The world has to be described in terms of densities, just like in quantum mechanics and probability amplitude. So that's true now both for classical mechanics, quantum mechanics, and also for stochastic mechanics. If you want to make career change and join the criminals on the Wall Street, they are all described by linear operations, and that's powerful and beautiful. So we have defined observables and we have defined averages. And now I want to give you a hint of how this formalism of evolution operators, nobody asked for these stupid operators, but it's very powerful, and it actually enables you to derive formulas, which once you're done, you realize you didn't need maybe evolution operators, but it's kind of as good as understanding how you get spectrum of hydrogen or helium in quantum mechanics. It has that flavor. So how do you go from this thing that, everything was tangible until this moment where I introduce these operators? What are these things doing? How do I get physical predictions? In Chaos book, this is chapter 20. What's time average? Here is how you can define time average. You can take your observable, make your observation a space point t, but you make them in trajectory where xt is you started at the beginning and you evolved on trajectory for time t, and you integrate over all time from 0 to t. And this gives you something I'll call integrated observable, so it gives you something that's larger than a, because you integrated on the trajectory. If you have a discrete time system like a known map, anything that's stroboscopic map, whatever, then you can only compute the value every time you see it, and then you just add up all the values. So that's like integral of the observable, where kth value is you start, and then you go time integer steps, f, and that's what you get. Now this has a very nice interpretation on a periodic orbit. It's easy to compute. So anytime you have a periodic orbit P, you only need to go once around the orbit because you already done the calculation. So it's the same thing as here. You go from 0 to 1 period, then you don't repeat because why would you? It's the same thing, just repeated. Or if it's a discrete thing, you go start at some point, let's say first one, go in p step period of a cycle called p. And then you have a nice formula for expectation value, for the average of your observable, or its expectation value on every periodic orbit, which is this integrated thing over a period divided by the period. Let's try to connect this stuff to our operators. So we know that a spatial average is done by starting at any point in your state space manifold A, running time t, and then dividing this by the volume of the state space. Which is just integral over the state space, which is the volume of M, of course. So if observable is just number 1, I'll get average will be number 1. So that's obviously what you need to do. And this depends on how far you go. So it's a time-dependent thing. Now, expectation value should be the most robust of all things, which is averaging over both time and space. So if you have an observable, you can do a space average of the time average of it. And that's a limit. So now you're in space-time. This is volume, and this is one-dimensional volume of length and time. This is in state space, and this is in time. You take a limit to infinity. You integrate in d-dimensional manifold over a whole manifold. You integrate to time t, but you take it to infinity eventually. And you look at x every place. So this is obviously the nicest thing that you can associate with observable. You start every place you average, and this is what you expect. Great. But how do you compute it? And that's what the chaos theory is about. It's about how to compute such things. There's one idea which is maybe technical, but unless you have it, you don't make much progress. And the idea says, you have to compute expectation value of something. But usually you also need to compute other things which are called moments. You know, you might want to compute expectation value of temperature square or something. There are good reasons in statistical mechanics. That's totally obvious. And we are really doing statistical mechanics right now. You know, that this is deterministic law is not so crucial. So the idea is instead, don't look at this, but to look at the generating function for all moments. A nice thing, but maybe not so obvious when you do it first time. Look at the exponential of your observable. It could be a vector observable, even tensor observable, and stick here letter beta, which in statistical mechanics has a name. It's called inverse temperature, but here is just a handle to manipulate moments, as you'll see, just a helpful intermediate variable. Divide this by volume, dx mu e to the b times ax. And why are you going in exponentials here? For the same reason why, you know, Gibbs and Boltzmann, everybody has to get exponentials. You know, this average quantity up here has a property that if I go for longer time, it just adds up. So it's additive in the exponential. And you're dealing with matrices, so things have to be multiplicative. The way you deal this is stick them up in exponential. And that's the only way to make things, multiplicative things, additive. That's a unique solution to that problem. So beta is just some auxiliary value. Let's now notice that if I want to compute expectation value of mu at time t, all I have to do is take a differential with respect to a, that brings a down, and then set the fake variable equals 0. Then this becomes this times identity. So if I know how to compute expectation values of these exponential functions, I will know, it turns out, how to compute expectation value of all observable and moments. That's why we studied this instead of what we thought we should be studying. So I look at this. I know that each one of these things grows proportional to time because it's time times its average. Average is, you know, some finite number. So at every x, I have an exponential. In other words, I'm summing over lots of exponentials. And you expect that sum of exponentials in a variable time is exponential. So maybe one is supposed to prove this. I haven't done that, but it seems fairly obvious. So we expect that e to the b times a, where a depends on time, should behave for large times as something that is kind of some constant factors, e to the t as some exponential which has to be computed, some number, and that number depends on beta, because depending what beta is, a way different parts of a differently. So it's a function of beta. And this can be computed by looking at b dot a, taking its logarithm to bring it down, dividing the time out, and taking limit t goes to infinity. Now, I seem to be lost a long way from home. I was doing some totally sensible thing of moving densities around, and now I'm taking you to look at averages of logarithms of expectation values of exponentials, and God knows, what is this good for? Well, people who know statistical mechanics know that this is great, because once you have such a thing, then we have kind of already shown, if I take its first derivative with respect to fake variable and set this helping variable equal to 0, then what happens is I bring down A. So I'm looking at limit t goes to infinity. I inherit 1 over t from here. But what is this limit? You know, this is integrated variable proportional to time. So this is actually what I want to get, expectation value of observable. So if I have this function, its derivative at beta equals 0 is just expectation value. But then, and that you really learn in statistical mechanics if you have a decent course, if you keep taking higher derivatives, you get things that you know you really care about. So if I take a second derivative of this S, then you know the first derivative will bring A down and the second derivative bring A down again. So I expect something that it will be proportional to this integrated observable twice. But when you compute this combination, you find out that they get subtracted from their expectation value, you know, so they're actually fluctuating around their mean. That's what this really is, 1 over t squared. And that's called covariance. It's a matrix with 2 indices called covariance matrix. And that tells you something about the distribution, you know, about not just what your observable is, but when I do lots of measurements of it, how it's distributed around its mean. And why am I teaching you all this? When one thinks about it a little bit, one realizes that one can compute all of these guys from the operator lambda t, you know, glorified matrix, which has spectrum, because every linear operator has spectrum. And we are very good in computing spectra of linear operators. So this circuitous thing says that if I have an operator, the simplest example is the one I showed you, Perron-Frobenius, which is glorified matrix evaluate time t. Its eigenvalues turn out to be all exponentials. The first exponential, the largest one, is the one I just told you, called S so far. But there are infinitely many of them. You know, there is S1, S2. And if I understand this matrix, glorified matrix, I get all its eigenvalues. And if I have these eigenvalues, I know how to predict all things that can be measured in the chaotic systems. Measure, I mean, on the time scales much longer than Lyapunov scale, when, you know, we have lost predictability. And you might ask yourself, but how? Well, there is only one answer. As far as I can tell, there is only one reputable textbook. Take Chaos book. And you don't need me for it because it's a self-taught course, course.1. And it's explained there. And the answer is very beautiful. You work, and you find out that if you know averages over periodic orbits and their stabilities, then you can compute averages of any observable to exponential accuracy. So it's an exact theory. There are no statistical approximations, nothing. You just work through it, get the answer, and then apply it to a system of your choice. That's all. I'm done.